All right. So I graded the exams, but I haven't yet tabulated everything and entered the grades or made any adjustments yet. So you'd actually prefer I do not give them back today, and I cannot give them back today because I don't have them with me right now. Because I'm going to see about giving back credit now that I've taken off everything that I'm going to take off. So that's just a quick little update for you. That'll be ready for you on Thursday. So Thursday we'll go over the exams. I'll pass them back, and probably we'll have a little bit of time to start the BOD stuff, so that plus next week for the holiday, you'll have pretty much everything you have to have for the next homework. I'm hoping. Worst case, we'll touch up a little bit of extra things after the holidays before the homework will be due. Okay, so that said, also we'll probably post a homework, I guess maybe Tuesday next week, covering this stuff and the biological oxygen demand type of stuff. So that's kind of that's the plan. Semester's winding down pretty quick.
Yes.
Time is flying. Okay, so today we're going to come back to this secondary wastewater treatment process. And this time we're going to take a look at it from a little bit more of a steady state type of analysis. So last week we took a look at what happens in a system where we're growing microbes, they're eating food, and the food is changing because it's being eaten, and the microbes are changing because they're growing on the food, right? It became pretty complicated. We had this one particular case where we had a pond system where we had stuff coming in and stuff going out, and X naught was 0, so we had some specific mass balance that we could ultimately arrive at given that, and we could solve some problems using that particular case. We'll come back to that to kind of take a look at it. Today, I want to look at a scenario where we can really control X much more readily, and we're operating at a steady state system where, while S has decreased because of the reaction, we're keeping things the way it is. I mean, and I guess in a sense, they were steady state in that former problem, but with the recycle, we have new controls over the mass balance here. So we're going to, adding this recycle line and adding all the other pieces to this feels like it's going to make it more complicated, but it turns out we have easier tools to deal with it mathematically when we make some assumptions. So one thing you'll notice, and we're going to talk through these assumptions in just a moment, is we're drawing a control boundary outside of the whole recycle system. So when we're analyzing the mass balance of the entire secondary wastewater treatment process, we just have one input and two outputs. Okay? Everything else in the middle is just stuff in the middle, right? That's inside our black box here. So we're going to talk a bit about it and the assumptions that let us draw up this mass balance. But at the end of the day, what's going to be really important is the fact that the clarifier separates bacteria. And so if there's not much bacteria exiting here, if that goes to 0, the X, then we have maybe some bacteria coming in, but not much. We're growing a bunch of bacteria, and then we basically control what happens to the bacteria by this one waste line. So we'll see by the end of the lecture today, this waste-activated sludge line, how much of this bacteria sludge are we discharging to a landfill or biosolids processing. That really controls a lot about our system. Okay, so we'll see that as we get going. Okay, so first assumption is this perfect clarifier. Mentioned this already, and I think we probably mentioned it last week, but if this clarifier works well, then the mass of bacteria, like whatever separable mass, will sink, then we have effectively, something close to zero going out here. And if we have zero coming out here, like I said, that simplifies our math. Now, there are scenarios where that becomes non-zero. Those are usually accidents. If you change the bacteria's condition, their growth conditions too much, if they have a different type of food, suddenly they get a lot of fatty acids or something, a different type of bacteria starts growing, producing filaments and stuff that catch all the bubbles and start causing flotation of the bacterial mass. That becomes a disaster because then you no longer have the separation here, meaning you can't send a bunch of bacteria back to recycle and control and provide plenty of, high concentration of X in here is pretty important because they're doing all the degradation of the food. So you no longer have control of how much food the bacteria are eating because you don't have control over how much bacteria you're keeping in the system. Then your food to mass ratio goes even further out of whack, and it's just problem after problem after problem. Not to mention you're discharging a whole bunch of bacteria out the effluent that not even, you need a filtration system rather than a disinfection step at that point. So there's so much bacteria going out. So all that said, we normally want and assume that the mass of bacteria is approximately zero leaving that. Of course, there's going to be some bacterial cells and all that, but for the sake of management, it's approximately zero. The next assumption we're going to make is that the clarifier has no effective volume when it comes to reactions. So, meaning we assume that there's no biological activity inside there because we're not bubbling air in it. If we were bubbling air in it, we'd have a hard time for anything to settle because those bubbles will capture the particles and lift them to the surface, right? So, in our clarifier, we say not technically V equals zero, but for the purpose of reactions, let's say V equals V aeration for the relevant reactions. So if we're looking at, let's say, theta equals V over Q, the V that we're talking about is the volume of the reactor, right? The volume of the aeration tank. So we can exclude the aeration, the sedimentation chamber, the clarifier, based on that. So we say, okay, nothing important is going to happen in the clarifier. Yes, technically there will be a little bit of biological activity. Yeah, they'll probably consume some of that oxygen, but we're just going to assume, set it aside and say, hey, if anything, it's a slight safety factor for us. We'll have a tiny bit more treatment than we thought. Okay, but effectively, we're not providing the oxygen. We're not doing any of that. So, and the water is not going to stay there for a terribly long time either. Okay, so that's the second assumption. The third is something that's not quite an assumption. It's just self-evident once you take a look at it, and that is when we separate the bacterial mass. That clearly makes a difference. The clarifier changes the bacteria concentration, but the substrate, which is our food, we're assuming is dissolved. So a gravity separation is not going to do anything to a dissolved compound, right? Molecules, if you dissolve some salt in the water, you're not going to be able to sediment those salt ions. You'd have to reprecipitate it somehow, so oversaturate it or something, and then you can get some of it. So when we have a dissolved compound, let's say S is sugar, let's say, it's in there, the sedimentation is going to do nothing for it. So this S here is going to be the same S everywhere after, right? So we'll have S coming out here, we'll have S coming out here, we'll have S in this pipe, and the pipe splits into two directions. That's going to be the same S here and S here. So even though we could maybe label each of these different, like the waistline, the recycle. We could label that something if we wanted. This as effluent. All of those are going to be the same because there's nothing changing the concentration between these steps, right? So all of those are the same, and you see them labeled in the diagram like that. I just want to highlight that all of those are equal, right? So that's just out there. That's not true for the X, for the bacterial concentration, because the clarifier, in a way, it's acting like a membrane, right? It's separating. It says, okay, X can only go this way and not that way. So X cannot get out of the chamber. It has to go the other way. In fact, a quick aside, there are such things as membrane bioreactors that swap the clarifier step for a membrane, and they keep all the bacteria on the one side of the membrane, and that's the way we control where they go. Since a membrane can do a better job at preventing bacteria to pass compared to a gravity-fed system or a gravity system, you can actually operate at higher bacterial concentrations, and that can give you better treatment. It's just a little bit more expensive in terms of infrastructure and the pressure costs to operate the membrane. So membrane bioreactors, it's a variant of our activated sludge systems. They're most common when you have big space constraints, and you have maybe a wastewater treatment system in the corner of a river and a railroad. I visited actually 2 different ones in Michigan like this, and they just built there because it made sense at one time, and now they need to expand capacity for meeting the needs of a growing community, but they have no land they can use. They can't build into the river. They can't dig up the railway to use that land. So what they have to do is they have to make a higher space efficiency operation. So what they've done is upgraded from activated sludge kind of with a clarifier. You can remove the clarifier altogether, and you can get more bacteria per area, per volume, in a membrane bioreactor, and therefore you can treat more food, more substrate, more wastewater. So that is becoming more common, and there's a bit of a cost trade-off there that will probably never fully go away because gravity is pretty cheap if you have the land area. But it's a good way to get pretty high quality wastewater treatment. Pretty much the same principles apply. We're going to stick with the clarifier system for now as we discuss this. All right, so then given that separation, my point here is that we have some X coming out this line, and this juncture is not going to change the concentration, right? So when I say XR equals XW, that's what I mean. If this is XR here, this is XW, those are the same, right? So again, should be pretty straightforward. Of course, XE we already said was 0, and so that also means that whatever X this is, which is actually just X right here, is not equal to XR, right? We know we've concentrated it because we've had separation in the clarifier. So in fact, we could say that for sure, XR is always going to be, or XW, is always going to be greater than X because we are getting rid of some of the water and keeping only the bacteria to an extent. That's what the clarifier is doing, right? So it would always make sense that whatever X that we are recycling is going to go, that's going back to the beginning, is going to be a higher concentration. That's all written here already. Okay, so those are kind of the operating assumptions we're making here. And that's going to let us keep good control of our system and really make sure that we have adequate control of where the bacteria are. So there's 2 reasons we want that control. One being we want to be able to control the growth conditions for the bacteria themselves. Last time we talked about that specific growth rate of bacteria and how important that was to know how quickly they're growing. Well, that's going to depend on each different type of bacteria. Each different microbe is going to have its own maximum substrate utilization rate, its own maximum specific growth rate. And so if we're not careful, if we don't keep a good range of how much bacteria to how much food they're receiving, we might accidentally get wrong kind of bacteria growing. Okay, so back to the idea of, well, what if we get sludge flotation and we get everything escaping? That's a really bad scenario, right? We don't want that. We would much rather have the sludge be sinking. So we typically operate and try to keep a standard food to mass ratio for that reason. That's also the reason we require certain industries to pre-treat their water if they're going to discharge into a municipal sewer system, because if they change the acidity, they could kill off a bunch of bacteria or promote the wrong bacteria. If they discharge something that's toxic to microbes, that would also be a big problem. So we have to essentially protect the bacteria that we want to grow so that they can eat all the junk. Now, the food to mass ratio here, we're going to define. This is a term we're going to use. This is an equation you'll have on your exam. This is not a typical ratio. This is just one term, okay? So when I put this in quotes, I mean, whenever we use this in class, leave it as F/M. I know it's confusing and awkward. This is the way the book's handling it. We're not going to distinguish between the food and the mass. It's in the equation. We'll see that in a moment. But this is basically a ratio of how much they get fed every day. So it's also a time term here. We do not want to multiply both sides by M or divide both sides by F or anything like that, right? Just leave it S/M just as it is. So apologize for any confusion that might cause. But what I'm going to say is this is just one term. Okay, so something to make note of for your formula sheet. You'll have this equation on it, but you need to know that we're just leaving it in that form. Okay, so what does that mean? Well, if we take the flow rate times the amount of food coming in, the substrate, the influent substrate, that's food per day, or food per time, right? That's a volume per time times mass per volume. That gives us mass per time. Right? So that's a rate at which mass is being added, and we're going to divide that by volume times concentration of bacteria. The volume times concentration leaves us with just mass. So that's a mass of food per mass of bacteria per time. Okay, so that's what we're talking about with food to mass ratio. So typical units would be something like milligrams BOD per milligrams VSS per day. Okay, we talked about the fact that mu, that specific growth rate, depends on the type of food. So if the type of food changes, the amount of food changes, we could have some issues. So there are kind of common practice F/M ratios that are used and that are known for keeping your bacteria. And this might be specific to some particular treatment plant happens to have this set of bacteria growing. And most wastewater treatment plants, with all of this biological activity, all of the different inputs from waste products and everything, you expect all sorts of bacteria and other microbes to be there, right? There's going to be millions and millions of different species of bacteria. But typically, with this type of culture system, you get a couple that dominate. And so you'll have most of your mass is made up of just, 2 or 3 bacterial species. Almost all of them. Something like 90 to 95% will be like 3 to 5 different species comprising the vast majority of organisms in there if you were to count all the cells. Of course, there's going to be other ones, but that's just typically how we operate and what ends up happening given how specific the conditions are. So we want to keep a good range for them and ultimately avoid that sludge flotation. Okay, so how do we control that? If we stop and think about it for a moment, the way to control this formula, so if F/M equals Q S naught divided by Vx, what can we control? Well, the flow rate is pretty much set, right? We have to treat a certain amount of water that just comes to the plant, right? So that's not really an option. That's just what it is. Likewise, the inflowing substrate concentration, maybe we could dilute it. Again, change, but that would also change this, so that wouldn't really make a difference, right? The product of these two is something we can't really change very much. Maybe we could add more food if we had to. That's not something we'd be likely to do. With maybe the exception of a case where let's say you're trying to remove nitrogen and they just don't have any carbon-based substrate. Maybe then you do. That's kind of a different topic. So you can't really change either of those. The volume of your reactor is pretty much set. It's not something you can adapt on the fly. So you're not planning to change your volume. So really the only thing you can change is X. So X would be a variable that operators could manipulate. And if we think back on our system, the control here would be to control how much X we discharge, right? So how much we discharge controls how much we recycle, which ultimately controls how much we have in our system. So if we need to control the food to mass ratio, we control the mass of bacteria. So I'll just write a little note. So we control F to M based on X. And I'll say using XR, so using the recycle. Okay, does that make sense? Okay, so relatively straightforward term here will be pretty useful. Next up, we have to talk about the retention time. We'll start with hydraulic retention time in our system. Already mentioned that the clarifier is effectively 0 in terms of volume for retention time. Yes, there is a volume there. Yes, the water remains there for some amount of time, but we're talking hydraulic retention time through the reactor. And we said that the secondary clarifier is not participating in the reaction, is our assumption. And so really, all we do is we use the volume of the aeration tank, and it's our very typical standard theta is V over Q, right? So theta is V for our activated sludge reactor divided by the Q that's coming through the entire system, right? Because we could stop and say, oh, well, is this the Q, are we talking about Q here, or this Q plus QR, right? Or, which Q are we using? And ultimately, if we take a look at our control boundary, control volume, we've drawn it out here. So we can say that Q equals, so that's what's coming in, equals what's going out, which is Q in the effluent and Q in the waste line. So that remains constant regardless of how much we recycle, and the volume of our reactor remains constant. And so ultimately, it doesn't matter how much we recycle. The total water flow through the system is going to be the same. That's Q. And that's going to be flowing through this particular volume that has a reaction happening. So it's going to maintain the typical V over Q, right? Just like we would normally think of it. Very straightforward, very simple. Assuming we have no biological activity there. Okay, so what about the solids? Because the solids, we certainly are changing. So here we're going to add a new term called solids retention time. Some you might see it as SRT for solids retention time. You might see it as theta C in our book for cell retention time, talking about bacterial cells. So how long do the cells themselves exist within our chamber? Got a nice, attractive picture of a recycle line coming back into aeration tank here. So theta C is going to change based on our recycling, right? Because we explicitly have changed the concentration by collecting the bacteria and sending it down this way. And ultimately, our recycle, our XR, so the X recycled, is going to depend on how much waste we send away. Well, really, it's QR that depends on it. X is just going to be whatever amount, this will be all the bacteria were separated and are now heading this way. So the flow rates just depend on that Q, the QW essentially, what we decide to use there. Okay, so theta C is not going to be equal to theta. So make sure that you recognize this. There's an important distinction here. This is not our hydraulic retention time. It's going to be solids retention time. And as we derive it, let's think about the fact that theta is V over Q. That is the amount of water divided by the amount of water per time, right? That's giving us a unit of time that tells us how long the water spent in the air, how much time the water spent there, right? So when we start talking about theta C, what we want is mass of bacteria divided by probably something like that mass of bacteria times time, or divide by time, right? Something approximately like that. So the way we can do this is say, well, if theta is V over Q, then theta C is probably V times X divided by Q times X, right? Because that converts us from just water into bacteria mass. So it's approximately going to be this, and with the caveat that we also have to pay attention to where the X is going, and so that leads us to this equation here to say, well, technically this theta C, that's going to be Vx, so that's what's coming in, that's what's in the system, and then dividing it by the Qx, that's going to be the Q going here, the QE, and the XE, plus the QE, the QW, XW. Because those are the two places it leaves, right? When we talk about theta, it's just Q over V over Q. If we had a theta in this case, we could write it as V over QW plus QE, right? Because the water's leaving in two directions from this map, from this picture. So that would just be another way to write our theta in that particular case. But we know that Q equals QW plus QE, so we could just put Q there, right? So that was not really relevant to calculate theta because we already knew that was the situation. Okay, so for this case then, we have QE plus QW XW. That's essentially capturing the bacteria, the mass of bacteria, divided by the mass of bacteria times the flow rates, which is going to be, or the concentrations times flow rates, which is going to be that mass per time. So it'll be mass over mass per time, giving us time. But we know that XE is 0, right? So if this went to 0, that just becomes Vx over QW XW. So then this gives us a very convenient way to say, if we want the bacteria to, on average, stay 2 days in the reactor, here's the conditions we need. And we control that with QW. So QW is something that we have a control knob on, and we can change, we can increase how much we're sending to waste, we can decrease how much we're sending to waste, and the result will be more or less recycled. Now, technically you could just say, oh, I'm not gonna send anything to waste, but then you're just gonna have an instant accumulation, not instant, but a steady accumulation of of bacteria, more and more and more of the sludge in your system, because you're never sending it out anywhere else. That's just not going to work, right? You have to eliminate that mass that you're accumulating. So you're going to find a steady state solution of constantly discharging some mass out the waste line. But if you decide to change it, then if you decrease, let's say, if you decrease this QW, this X will increase given the same solids retention time. Okay, so with that, we now have two equations to deal with kind of the bacterial concentration and how much food they have, and kind of the ratios between the two. And it turns out that controls a lot of what we care about for our activated sludge systems, and we don't typically have to go into the mass balance sort of situations that we did for the pond scenario, because we have this control in this manner. Okay, so I'm going to take the rest of the time today and go through an example problem with you. I'll talk through a few steps. The beginning of this problem is really very much the same as what we did last time. So I'm just going to jot a couple notes down for you and let you do that on your own time if you'd like. So essentially, well, let me just read the problem, you'll see. So we say, consider a wastewater treatment plant that is being renovated to include a return activated sludge line, RAS line. Assume the influent MLVSS. I'm not sure if I mentioned this, but MLVSS, that's the technical term. It's a mixed liquor, volatile suspended solids. Just another term for X. Okay. Kind of sounds gross. Just the term liquor actually means some mixture, basically. So it's a mixture of wastewater and bacteria. So that's often the term that people will use. So when you see MLVSS, that's what they're referring to. So assume the influent MLVSS concentration is 0 without the recycle line. So that's saying X naught equals 0. And the following parameters are known about the reactor, which acts as CSTR. So it gives us lots of parameters we can use. And then part A says, draw a schematic of an activated sludge system before and after the addition of a recycle line. So actually, I'm going to have you start here and take a minute to draw your impression of what an activated sludge system would look like before and after the addition of a recycle line. Just to make sure we're kind of tracking on the same page here. It'd be good also to label the different flows. Okay, so hopefully you choose something approximately like this, where we have, if you wanted to draw the primary treatment, you'd probably have some sort of sedimentation tank, then send it to this spot. Kind of optional there, because really what we're talking about is the what happens here, right? So you can neglect that part if you'd like to. But once you get to the activated sludge system, that really comprises the aeration tank, what's coming into it, what's going out of it. And in the case of a recycle line, that means you have to have a clarifier to condense the sludge and recycle some of it, right? So if you don't have that, maybe you would have a clarifier, you're just not recycling. So I guess you could maybe draw a clarifier here just without a recycle, that would be fine. But, you could conceive of a wastewater stabilization lagoon, in a sense, as just an activated sludge system there. Those are a little bit of a separate topic, but one way or the other, you don't have the recycle line, or you do, right? So after we're adding that recycle, and that entails we have the clarifier and all of that. Okay, so part B then is essentially part A from what we did last time. This was with the no recycle system. This is acting just like it's a pond, right? That was the CSTR. It's like a pond, or rather it's like a tank. The pond was like a tank. We have these growth conditions, all of that, and we said, what is the substrate concentration before the recycle line was added? And we said we did a mass balance on X counterintuitively to find S I gave you the equation for that. You have that. That'll be on your exam. Again, specific for a pond type scenario where we do not have recycle. So if you'd like to do that, you have all these parameters. Absolutely feel free to do so. Part C then, just as before, this is an efficiency where we say what we started with minus what we ended with divided by what we started with times 100% is going to give us our removal efficiency. And then part D was, okay, what is the MLVSS? That's asking for what is X. What is the X concentration in the no recycle system? So this was a mass balance on S to find X. Now that we knew something about the substrate concentration. Again, we did this last time. That was the last part of the problem at the end of the class last time. So I'm not going to stop here and do that. That's where you would use a lot of these parameters about the decay coefficients and maximum specific growth rates, all of that. So I'll leave that there for now. Again, maybe good practice if you wanted to go back through that again. Instead, I'd like to move on and say, for part E here, we have a question. If the sludge produced has a concentration of 12,500 milligrams VSS per liter, which is now recycled through the new recycle line at a flow of 150 cubic meters per day, what is the resulting influent, so this kind of a new influent, MLVSS concentration in milligrams VSS per liter entering the aeration tank? And I give you a hint here that you should refer to your drawing and to not overthink the problem. I'm giving that hint before because I have given this portion of this problem on the exams before, and routinely students overthink it and get it wrong. Okay, so take a step back. I'll go ahead and write up the formulas that we learned today, but let me just remind you to not overthink and just look exactly for what this is asking you and what you need to solve for it. Okay? And I'm going to give you a few minutes to think on that. Got plenty of time. You guys have answers? Just blank stares? Do you feel like you have an idea of what's going on here, or do you just not know where to start? How are you feeling about it? Not sure? Okay. So this is what the problem is asking for is something you've known how to do before walking into this class. Okay? So you're really, you're probably overthinking it. So I'd encourage you to really think about what it's specifically asking for. And I'm going to go ahead and actually coach you on that. Specifically, it says, what is the resulting quote influent MLVSS? That's X, right? Yeah, I understand that's something you wouldn't know before, right? But so if that's X, what's the resulting influent X entering the aeration tank? So we're talking about some value here. I'm going to say X naught prime. That's what we're looking for. Okay? Does that make some more sense? All right, see if you can get an answer for that. Really, we're just kind of honing in on this little spot.
What do we know about what's primarily going in there? Because this is just literally Q in is Q out, but I don't know what Q in is. Or is it just zero because X is not zero? Right? So
knowing what the variables are.
And let's make like flashcards.
Yeah.
Or something.
Is there a conversion I can do
For the Q,
Oh, that was supposed to be that.
not going to need that. Cubic meters is a volume, milligrams is a mass.
Yeah.
So you can't convert. I mean, if you're talking about like the mass of water, you could convert with the density or something, but you shouldn't need that for the problem. All right. So as you might see, I kind of wrote up a bit more here, trying to kind of hone in on just this little spot. If we treat that as a control volume for a mass balance, we have two streams entering together to make one final stream coming out. Something we did very early on in the class. So this is what I meant by try not to overthink it. If you could identify where the pieces are going, what we're actually looking for is this actual amount of X coming into the reactor after that recycle line has joined. We have some new flow rate that has that added recycle flow and some new X concentration added from that recycle line. And it turns out that this system, what I was asking for is just a very, very simple mass balance, especially because the X naught is 0. So this term, the inputs are the Q X naught, that goes to 0 because X naught is 0, plus the QR XR. So we're just talking about mass per time here with the flow rate times the concentration, is equal to this X naught that we're looking for times the total volume. So we've done that quite a bit. So this is what I meant by don't overthink it. You didn't need any of this stuff. If you can identify and had some chatter over here about variables, like understanding the variables, that's probably the best way to study on the exams is to take a look at the formula sheet and practice identifying where these variables are coming from and what they mean. I think would be very helpful. Okay, so to solve the problem then, we get this mass balance and we can fairly directly say this thing that we want to solve for is going to be QR XR divided by the Q plus QR. Maybe we can simplify a little bit and divide everything by QR. That doesn't really matter. So we have QR that was given to us, 150 cubic meters per day. We have Q, which was 0.01 cubic meters per second. We can multiply that by 86,400 seconds in every day and get just basically 864 cubic meters per day. XR was given, that's 12,500 milligrams VSS per liter. So what we're going to end with is a flow rate times a mass concentration divided by a flow rate is going to give us units of mass concentration, right? So this will be, if we put in the numbers, I think it's 596, is that right? Somebody could check me.
So it's literally 150 by 12,500, and then divided by the summation of 1250 and 861.
Yeah. Is that what you got?
Yeah.
So it should be, let's see. So QR times,
We don't have to worry about converting it to meters of cube.
so the question here is why don't we worry about converting this guy to cubic meters? Well, that's going to be because we want an answer in milligrams per liter, right? So when we have that concentration here and we need to divide it by 150 cubic meters per day plus that 864 cubic meters per day, that should be giving us the 596, if I'm remembering correctly from this morning. Did you guys get that? Oh, I'm sorry. That's the next problem. 1849. Yeah. Okay, well, now you know the answer to the next problem. All right. Okay, with the right number there, makes sense? Okay, do you see that overthinking thing? Was this helpful to let you run into the overthinking challenge, or? Okay, good. Because that's kind of what I find here is for this type of a problem, a lot of the problems in the class generally, especially for those who are not as familiar with environmental problems, identifying where the pieces are coming from and what they mean is, on that conceptual level is quite important. Okay, so then part F here says, in the new system with the recycle line, so again, in the new system here, the resulting food to mass ratio is 0.58 milligrams BOD per milligrams VSS per day. What is the MLVSS, the X concentration in milligrams per liter VSS? So it's asking what is X in our system. And again, our system we're referring to here is a recycle line system. We're looking for X. Okay, so take a minute to work on that. I'll remind us here.
Alright, so the radio station is yes. Well, how about the other? There's a Q from prior, Q from that 2.0.01. So really the last our new Q's would be this text on Q over here. So it should be 150. Right? We're on the right track here.
What was the question?
Is our new Q going, so we're clearly using this first equation for this. The FF equals QS.
Yeah.
V over X. So is this Q double plug in here going to be 150 plus 864? We're building on the last one.
So
Or is it going to be Q of 0.01 so it's going to be the reactor?
all right. Question here, I think is useful for everybody. Do we need the Q here or the Q here? It's kind of the question. And what I'm going to say is, if you think back, and if you were to take a look back in the text, I'm just going to flip back real quick and look at how we were talking about the system in the first place. How are the Q's labeled? Because we were deriving the equations from basically this figure, right? The unlabeled Q is the Q that just goes straight into the to the whole system, right? And the reason that we were talking about the assumptions and things is the hydraulic retention time. If we draw that control boundary on the outside, that's the Q, that's the unlabeled Q, right? That's kind of what matters for where the water is going. So think about that as you decide what Q this is referring to.
That is like, I'm looking at the well, how about that's what else do we know? Like, what else is that's correct? That's not. So we. So. And X. Back where. We don't know what that's. You know, that would honestly make sense in the initial. Thank you. Well, then how about we do the units, right? That's all right. Yeah, we're good. The unit first one, that's at 220. Concentration. Multiple concentrations.
Okay, so this problem's fairly straightforward. Again, some potential confusion spots about the variables and things. And my intent was to remind you that for a system like this, we're drawing the control boundary outside of the recycle line, meaning the Q that we care about in a kind of the bulk big picture sense, especially for hydraulic retention time type purposes, is the Q that's going into and out of the system, right? So that's kind of agnostic to whatever recycle happens. The water, ultimately spending on average some amount of time there. So when we're talking about the amount of flow rate, especially like how much food is reaching the bacteria, that Q times S naught, that's going to be this Q out here and S naught out here. Okay, so, and that pairing, by the way, if you were to use the recycle Q, you'd have to also then pair the S that's right here. It would just get quite complicated, and at the end of the day, that's all inside your control volume, and so it's kind of moot, right? It's sort of useless and gets potentially recursive in itself. So having the Q S naught outside is quite convenient. We have the volume of the reactor, we have the influent substrate concentration, just a matter of finding it there. We have the flow rate. I converted the flow rate into days again, so that's 0.01 cubic meters per second times 86,400 seconds in a day times 220 milligrams BOD per liter for the substrate concentration coming in, divide that by our volume of the reactor, multiplied by the F to M ratio that we were given, and essentially I took the food to mass ratio equation and I divided both sides by the F to M and multiplied both sides by X to get a solution for X here. So we do that, and now, if I'm remembering correctly, this should be, somebody can correct me if I'm wrong, 596 milligrams VSS per liter. Good? All right, any questions or issues on that? So again, not super complicated. It's just a matter of understanding what the system is set up like. So in a strange way, the adding the recycle line kind of simplifies what we have to deal with. All right, so last problem, well, almost last problem. Probably the last one we'll talk about today. So what is the flow rate for the waste sludge line? And we'll say we're not going to worry about this assumption here. That's in case, like, if I gave you this on an exam or something, and you didn't find the other one was reasonable, let's just say the X is 596. And we are asked for the flow rate of the waste sludge line. So let's draw it up one more time. Remember how we labeled it. The waste line is here. We were given earlier that XR was recycled at 12,500 milligrams VSS per liter. Right, because we know that XR is going to be equal to XW. So there's no difference there. sounds like it. I'm not sure what exactly you're thinking, but
So
if it were me, I would see the take a look at solids retention time of 8 days here and say, oh, okay, so what we're looking at is we need to solve for QW, Vx divided by theta C times XW, and I think we've got everything at that point. So it should be the volume 550
yeah,
cubic meters times the X that we solved for, 596. Divide all that by 8 days times XW. The units here should cancel with the milligrams VSS per liter, and we'll be left with cubic meters in days. So that's decent flow rate units. And we can say so we should have a QW of 3.28 cubic meters per day. So with a wastewater treatment plant that is processing 800, almost 900 cubic meters per day of water, three to four of those cubic meters we're going to waste, essentially. Does that make sense? Any questions?
because they're both so much.
No issues? All right. So the last little bit of this problem was a hydraulic retention time problem. This is just real quick. Theta is V over Q, and it's going to be the same before and after because we said that clarifier is not changing anything. The recycle line doesn't matter. We draw the control boundary outside of it. And so that's literally just that 550 cubic meters divided by 0.01 cubic meters per second. Okay. All right, so that's all I've got for you today. We'll go over the exams and probably start the BOD stuff on Thursday. See you then.